This is the world's lightest solid. It's more than 99% air. Yes, that's more air than these. So why do we actually want this object to be so empty? Are we trying to make it compete with Buffalo's Super Bowl trophy case? Surprisingly, no. We want the material to be so empty that it has incredible properties we don't usually see in other solids. Oh yeah, and this solid's called aerogel, which fits it perfectly since it's mostly air and it's not a gel. Thanks, Kistler. Just kidding, it's actually a fantastic name once you understand the unique way that the solid form of the aerogel is produced using a gel. Gels are part liquid and part solid. Think about Jell-O. I can destroy some of the solid structure of the Jell-O by smushing it, and it starts to behave more like a liquid. See, it has a harder time withstanding shear stress and deforms more under its own weight. However, that's just breaking some of the structure of Jell-O. If I truly wanted to make it a liquid, I can heat it up. Now it can hardly withstand any shear stress. Now this is great and all, but aerogel isn't a gel turned liquid, it's a gel that becomes a solid by removing only the liquid part. The complex and unique way that this liquid part is removed from the gel in such a way that the solid structure is undamaged is what makes aerogel so difficult, but so magical. Depending on your background, you might know that you can replace the water in Jell-O with other liquids. For aerogel, you do a type of solvent replacement as well, getting the pores to be filled with ethanol instead of water. Then you need to heat and pressurize the gel to above the critical point of the solvent. The critical point is the pressure and temperature at which you can no longer tell if a substance is a liquid or gas. After reaching the critical point, you need to isothermally depressurize. Supercritically drying the liquid is critical to the operation because it avoids the accumulation of stresses that normally comes from an abrupt phase change. Even after all these careful steps, you're left with a final product that's weaker than the screen of an iPhone 5C. There's many types of aerogels and some are stronger than others, but I chose to oversimplify one technique and one recipe of aerogel just for simplicity. Go to aerogel.org if you want to learn more. Anyway, that's technical enough. Now let's smash this fragile silica aerogel with a hammer in slow motion. Okay, that was fun, but I'm getting distracted. I still haven't answered the question, what's the point of aerogel? And for that, we need to understand aerogel's unique properties. After the liquid is removed, all the super tiny air-filled pores that are left behind actually make aerogel a better insulator than air itself. So it's mainly used on rovers and applications that need absurd amounts of thermal protection. Look at how good it is at protecting my finger. As you can see, the pan is much hotter than the surface of the aerogel. Silica aerogel can also be made hydrophobic, just like hydrophobic sand, which absolutely refuses to get wet. Look at how the water just streams off of this chunk of aerogel. It reminds me of the inverse Leidenfrost effect that I showed you in another YouTube video on dry ice. If I apply some silica aerogel to my hand, the water runs off in a similar way. Another cool thing about aerogel is that it emphasizes how color is not an inherent property of something, but rather a perception of it. Aerogel scatters light in a weird way that often makes it look bluish, but when held up to a light or the sun, it appears much more yellow. Thanks for watching to the end, and I'll see you next time.